Perfect. Well, good afternoon, ladies and gentlemen. It really is a great pleasure to represent many colleagues in this room. And energy, I do believe, is the most serious challenge that we face going forward in the planet. And in that regard, I use a quote here from a Nobel Prize winner, but you only have to pick up your recent Economist or the New York Times or look anywhere in the media and you know that this is a growing concern of everyone. Largely because we face what that popular phrase is of a perfect storm. The perfect storm being this first aspect of supply. Our supplies are reducing. And as shown in this slide, not only are our supplies reducing, but again, we all know in this room, since we read a lot, that many of our oil supplies are in politically unstable parts of the world, and a small change makes a big difference. So, for example, you can hear that I'm also an immigrant, and I have one of those funny English accents. There was a period when the natural gas could be purchased from Russia, but after the Yucca affair, there was a big reduction in that supply, which had a big impact on our energy resources in England, and it then began to push our emission levels up because we had to go back to using oil and coal. So there are very delicate balances in our world society. At the same time, this next slide shows that the demand curve is increasing radically. Over the next 50 years, we expect the demand everywhere to increase, and that's especially underscored by this next slide. Forgive me that it's a bit techie looking, but this is a really interesting slide. It's really worth looking at the axes on this curve. Along the bottom of the curve, it basically shows you how much energy we use per capita in different countries. The US and Canada are on the top right, and the European countries are in the middle. Don't feel badly about your Canadian friends like the Chancellor. It often means that there's a very large industry like aluminum smelting that uses very large amounts of energy. But nevertheless, you can also see there's large numbers of countries on the left-hand side of this curve that really need to be brought up in their standards of living. And this curve from our colleagues at the Lawrence Berkeley Labs shows that the dotted line is about the kind of threshold mark from where you move from a challenged society to a more wealthy one where healthcare and education and hospitals are better. So when you start to use about 4,000 kilowatt hours per annum of electricity, that's a kind of a threshold mark of a safe society with water and energy and so forth. So you can see from a supply point of view that all of the countries towards the left-hand side of this curve are going to want to move up. And then, understandably, as we increase the demand and increase use, we then begin to impact on this other aspect of the perfect storm, the global warming and the emissions issue. And that's one of the things that we all say differentiates this energy crisis from the one that was the Arab oil embargo in 1973. Then we really focused on energy increases, but we weren't quite so concerned at that time about the impact on global warming. So any solution that we come forward with has got to mitigate levels of carbon emissions in order to provide balance in the universe. So that's where this perfect storm comes from. The supply, the demand, the political insecurity, and the impact on the environment. So that's a key element of how I want to structure the remarks that I'm going to make. How we're going to do that is to focus on two key strategies, one of which is to do with efficiency and much more conservation in the civilized countries that really use a lot of energy. The other areas, these 2 through 5, are renewable and carbon-free environments that will allow us to increase our supply whilst not impacting the environment. Now, next to this, on the right-hand side, is an interesting curve. If we carry on with what people call business as usual, our carbon emissions will follow this top curve. And as we go to 295 throughout this century, that will have some dramatic impact on the environment, which is not the topic of my talk today, but most people in this room know what that means. The ideal case, then, is to create these new environments and follow this lower curve where the emissions to the atmosphere are reduced. So the rest of my talk is about providing these solutions on the left in order to achieve these reduced carbon emissions on the right. Colloquially, you could say it's having your cake and eating it too. And so the rest of my talk is going to be about shaving off those various areas. First of all, I'm going to talk about conservation, and then I'm going to follow it with the various shavings off that comes from renewable energy, nuclear energy, coal to gas substitution, and carbon capture. And all through CITRIS, it's a great honor for me to realize I have wonderful colleagues that are attacking these different areas. So this broad portfolio of activities will answer this perfect storm problem. Let's now then move to the first topic. I hope I've set the stage now. If you fall asleep, I think that's unusual. I got a very strong, loud voice, as my wife keeps telling me. But let's go through those 5. But in the unhappy event you do fall asleep, I think you've got the basic idea of the CITRIS mission in this area. So, power-aware buildings. At the bottom here, too, I've acknowledged one of our founders of energy efficiency on the Berkeley campus, Arthur Rosenfeld, in 1973, with colleagues, was a big influence on Berkeley strategy in energy, and began the efficiency buildings at Lawrence Berkeley laboratories and on campus. And that all is about making these power-aware buildings, meaning that in the crisis we need to face in order to reduce consumption is shown in this curve here. Again, here's another curve, so forgive me for showing you graphs in a sort of a general talk, but this is the way in which we as Californians used energy in around the year 2000 and 2001. Along the bottom axis are the months going from January to December. On the y-axis is the peak loads, not your personal load, but the peak load for the day. And not surprisingly, you can see that during the summer months, those hot, sweaty months in the summer, there are these great over-demands for air conditioning. Now, that's basically like a traffic jam on the Bay Bridge. Everybody wants to get there at the same time. Everybody wants to use air conditioning at the same time. So we want to reduce that. And how we're doing that in these large CITRIS projects, I have many colleagues that are working with me on that topic, and good friends at the California Energy Commission, Ron Hoffman and Arthur and others. What we're doing is building these ad hoc self-organizing networks to create price signals that go into our houses from these wireless infrastructures that will tell you in the middle of the afternoon, electricity is much more expensive. This is not a good time to do your washing. This is not a good time to run your pool pump. And if you're really part of this, you want to make your air conditioning a little uncomfortable, a little less comfortable, in order that you reduce your usage. And so here's a cartoon of myself and my wife in my kitchen. She's always got cold feet. So I put one of these little sensors right next to her to improve my marriage whilst we're doing this technology rollout. And just to give you some idea, I'm going to walk forward at this moment. I have one of these little guys in my pocket. You can see, those of you in the back, you won't see it. But you see here, what I'm basically holding is about the same amount of computer technology that my sort of 1990 IBM would have had, all rolled into a very small device about the size of a quarter. It has a computer chip on the front, wireless radio on the back, and a variety of places where you can attach sensors. And so you can see the general idea that my house will become wireless aware, that input signals will come from PG&E and the other IOUs in California, and we will run our house based on that kind of information related to the cost of electricity. And as Shankar just showed in his recent slide, that is beginning to get traction with PG&E, Southern California Energy, and San Diego Gas and Electric. They're already beginning to install these wireless meters, which are shown on the top right. And our job in CITRIS is to make these technologies for the wireless meters, wireless thermostats, and wireless infrastructure much more inexpensive. And that's these smaller modes that you see going up into that picture there. The other aspect of fuel efficiency is very much run by my colleagues in mechanical engineering. Here is an example of a tiny motor. Its objective is to have this miniaturized rotary engine for portable distributed power. and it's very well designed. It has a very small number of parts. A key element you can see in the middle, it can run on a wide variety of fuels. And the interesting thing that comes out in the end, that a tiny motor, not much bigger than a sugar cube, 1 cubic centimeter, has enough to power a small environment of 33 watts. Well, that's not as strong as this searchlight that's bouncing off my head right now, but it's certainly in the same ballpark of these lights in the ceiling. So you can see that these miniaturized power sources are really beginning to take play. Shankar mentioned Prime. This is another exciting mechanical engineering project studying combustion. The fascinating aspect still of our combustion environments is that we have a relatively inefficient combustion process in most engines. A lot of the connections between the incoming fuel and oxygen and the ignition is still leaving us with a lot of residual material inside the piston. And my colleagues like Bob Dibble are working on these homogeneous charge compression ignition engines where all of the incoming gasoline or all of the incoming diesel is fired at once and gives you a much more effective engine. Plus, it doesn't lead to nitrous oxide and other emissions that have to be dealt with your catalytic converter. Another interesting thing, this is just an interesting fact, that most of us, especially in California, you see more electric vehicles being driven. There's a difference between a plug-in hybrid and the kind of hybrid which is a Toyota Prius, but even now we have these 50 mile per gallon Toyota Priuses, and if we all drove these plug-in hybrid electric vehicles, a substantial reduction would occur in American usage of gasoline. Finally, in this particular area of sustainable transit, we all sit on, everybody in this room sits on the Bay Bridge looking at other people in cars thinking there must be a better solution to this. And my colleagues in the Institute of Transportation Studies, which is based in civil engineering, have had the luxury of completely redesigning a transportation system in this area of China. And what they've done in these maps that are laid out here is really made sure your problem on the Bay Bridge is somewhat solved. And I realize there is, when I sit there, I realize that if I'm going to a business meeting in San Francisco and I can get off the BART and be right there, well, then I'll take BART. But if I've got to take those subsidiary kind of routes out to North Beach or down to South of Market, the buses never connect. I can never find a taxi. It's pouring with rain, and I'm really frustrated. And so next time I take my car. So what is really needed in these things is to have an efficient connection between the BART system in the Bay Area and these distributed buses that would, for sure, you would know when you got to a BART station in San Francisco that a bus would pick you up or a taxi would pick you up and take you where you want to go. So this project is all about moving people around in the right way. So that was my first slice. I missed off many other wonderful colleagues that I could have talked about. Jim Evans may have come into the room. He's working on energy efficiency in aluminum smelter. Van Kerry may have come into the room somewhere. He's working with Hewlett-Packard on energy efficiency in these big data sensors. And, you know, Google has just moved its big server farms up to Oregon to take use of the hydroelectric power up there. But Van and his colleagues are trying to do the best they can with minimizing energy use in these big servers at HP in the Bay Area. So there's a very large number of colleagues working on reducing the use. And that was my green slice. Okay, I take a breath and I go on now to alternative fuels, which you heard a little bit about today in the context of these wonderful colleagues at British Petroleum who are interested in starting a large center somewhere in the international community to address renewable fuels. This is the key slide that our Helios colleagues use. And what's key about this slide, there's a lot of arrows on this, but just try and focus in this short talk on the three ways here of producing energy from the sun. Obviously, and Arnold has just announced the 1 million solar homes. Obviously, one key element is to get more solar power, and that's the bottom line, the electricity. And then across the top here is the possibility of growing these plants that you heard the Chancellor mention through this cellulosic route in order to produce these wide variety of fuels which are interchangeable. So let me just talk about these couple of routes in this renewable area for a while. Willie Nelson and many other famous people have promoted the biodiesel and biocorn, and that has been going from these monocultures from some time now, and about 3% of US auto fuels are using ethanol from corn. The small problem with that is that the fossil fuels is still used for the fermentation. So colleagues in civil engineering like Tad Pasek and others that are in the room right now have really tried to understand the full energy use of those kinds of ways of producing ethanol. And so what's been going on in more recent years is that these cellulosic sources, which are like switchgrass or poplar, are a little bit more effective in reducing greenhouse gases in the environment, because during the growth of those plants, they're woody kind of plants, and they absorb carbon dioxide from the atmosphere. So when you do the full energy balance, these kind of cellulosic sources for doing this kind of energy production are on balance a little better. And actually, if you're a subscriber of Science magazine, just this week on the front page are these prairie grasses which can be grown in a non-monoculture way in order to produce these kind of environments, and it seems like the results from these prairie grasses are also very effective in this environment. Let me give you a snapshot too on microbial fuels, which Beth and others are working on. And you know, I have to say, as a scientist in this area, I feel really honored to be part of CITRIS, and it's here where I'd like to take my hat off to Richard and others, and Dado, the Banatel family, Dado, for starting CITRIS with your vision, because some of these things are genuinely exciting. So exciting, when I talk about this to my family or to people on an airplane, it seems like magic. Okay, so you're looking at this slide, and there's this boring little piece of green algae in the middle, this Brachiococcus browni algae. Do you realize that that little sucker can actually produce biodiesel? In its own DNA, it produces, with sunlight and CO2, it makes a very, very slow dribble of C15, C18 dribble. But it does it so slowly that it would take you weeks to make an egg cup full of the thing. Now, moving along though, coming to this other bacteria, this one here mentioning Chlamydomonas, that can replicate itself very, very quickly. So here's the key thing. This is an exact, perfect example of genetic manipulation, where if you combine the DNA in the correct way, there's the possibility that the first algae that I showed combined with this second algae, one of which can produce diesel, other of which that goes very quickly in the sunlight and with CO2, will produce these materials very, very quickly. And that's the key element of some of these new environments that we're looking forward to. So Jay Kiesling and many of our colleagues in bioengineering have been doing the same thing for the degradation of lignocellulosic material that I mentioned before. So instead of doing it with lignin, or worse still with fossil fuels, we have the opportunity of taking these woody products and using these different ways to produce ethanol and these other mixtures of interesting hydrocarbons. And the idea of the algae and working with the genomes of the structure is fascinating. We have many companies involved in that. The Genome Research Institute is in Walnut Creek, who are studying the way in which the genome of those algae are described. That hasn't been fully worked out yet. And so those are the exciting things that the Chancellor and Beth mentioned before that are being centrally addressed in these projects going forward. The other aspects of alternative power are thermoelectrics. We are using these thermoelectrics to power many of the wireless sensor networks that you mentioned before. In the aluminum smelting, for example, the smelters are very hot, and you can power the electronics from a thermoelectric effect shown on the right. Here are some of the examples that colleagues like Arun Majumdar have made. And he are working on improving the Carnot efficiency, really basically the output from these thermoelectrics. And there are the best materials at the moment are like these exotic bismuth telluride materials, which are very expensive. And over time, we're trying to get the same kind of efficiencies with much cheaper inorganic materials. Coming now to the alternative power from sunlight, Paul Alivasatos, another one of our close colleagues, has been working on increasing the efficiency of solar cells. I chose an example here of a plastic film solar cell for him, which is really being giving very good efficiency because it's impregnated with these very small cadmium selenium nanorods, selenium nanorods. So why is nanotechnology so important? For those of you that maybe don't, you see the word nanotechnology and you think, okay, it's very small, so what's the big deal? Well, here's the big deal. When sunlight comes in through the top of this, through the indium tin oxide, which is a transparent material on top of the PV source, the excitons in this region, what's happening is that electrons are being bashed out from the valence band into the conduction band, and temporarily these excitons, which are positive and positive holes and negative charges, are temporarily available to deposit onto the nanorods. Now, what's interesting, if that doesn't happen very quickly, then the Coulomb forces just bring them back together again. So in this next slide, here's the exciting thing. You see what Paul and his colleagues have done is that on the cadmium selenium nanorods, they put these dots. What that does is increase the area. So the nanoparticles create much more surface area so that when the excitons are available, as shown in these slides on the left here, they can be captured much more quickly because there's more surface area, and this gives much more absorption and gives you more effectiveness. So here already we're seeing that the combination of clever science and clever structures, as is shown here with these nanorods and nanodots, as shown on this slide here, gives you much more effective PV efficiency. The most ambitious project that they're working on is shown in this slide, and I'll just try and go a little slower here. On the left side is the way in which most plants do natural photosynthesis. The green blocks have the light falling on them. The photons are falling, those yellow arrows at the top there are the falling on these parts of the plant to create photosynthesis, and then naturally enough in most plants that process slows down once they have enough material, and then these other areas of the plant begin to produce the materials that the plant needs to live, especially water. And so what Paul and his colleagues are trying to do is a very exciting project. They're trying to build these fabrics where you're looking face onto these fabrics, and these little hexagons here are various structures where they're isolating parts of the material that can mimic the plant's additivity mobility to optimize this photon absorption. And then second parts of the plant are using these cyanobacteria materials that create the water. So just like the things that might be going on over here in this natural state, they're trying to provide pockets over here which do the same kind of thing. And then these photoelectrochemical cells at the nano level will be there to create materials. A very advanced idea, and this is what a key element of the next Helios project is about. We have a wonderful nuclear engineering department coming to this next phase of my talk. And on this couple of slides here, I really want to stress that our colleagues in that department have contributed as much as anybody in the country to the safety and the designs of some of these smaller footprint boiling water reactor nuclear power plants. And the 20% of electricity that's now being used in the US will begin to increase over time. Now that my colleagues in those departments, the chairman, Yasmina Vucic, is here right now to take questions over the break, and they have made big advances in this Yucca Mountain repository. Notice that it's only the US and Finland that have decided where their repository sites are going to be. But because of the increased safety measures, as you can see in the sort of smaller print here, more nuclear reactors are being designed in the US, more are in the queue to be approved by the Nuclear Regulatory Agency, and in future, I'm almost certain that nuclear power is going to be a bigger part of the American landscape as it is in France and other countries that are more related to nuclear power. Just in my last 5 minutes, I want to stress, sad but true, the coal situation will always make us somewhat dependent on coal in the near-term future, and that's where a lot of science is needed to be done, again by colleagues around CITRIS. At the moment, the kind of general picture is that in the US, it's 50% coal, 20% nuclear, 18% natural gas, and about 7% hydro. But as I said somewhat comically here, unfortunately, coal is still dirt cheap. And if you compare it to these other things like natural gas, fossil fuel composites, and crude oil, it's still the cheapest way to go. And it is alarming that the newer economies like China and India that are so desperate for new energy are still building coal-fired power plants. And there's a lot of international collaboration that we need to take leadership on to make all of us work together to reduce our dependency on coal. So colleagues in mechanical engineering, civil engineering are working on these various routes. You see this one comes from coal pulverization through to electricity, but there are these other routes that are shown in this slide that can produce liquid fuels, synthetic chemicals, hydrogen, and so forth. Carbon capture and storage is another thing that's very interesting and is part of many of our colleagues in CITRIS. You know, there are new power plants that use coal being built all the time. There are 2 being built right now in the Ohio River Valley that I know something about since I used to be a professor in Pittsburgh. I know where those sites are, and they have already been designed to be carbon ready for sequestration. And what that means is that in the exhaust ducts, there is the opportunity to capture the emissions, to mix the carbon emissions with amines. The hydrogen and the oxygen go off into different places, and then there's an opportunity to either liquefy or solidify the carbon emissions. And these projects are also very much part of our civil engineering environment because they have to be safely stored either underground, as shown on the left, or undersea, as shown on the right. And this is a topic that obviously I would talk about with more time. So the last couple of slides, as I said, our CITRIS solution is to focus this wide range of faculty throughout the 4 campuses. Merced, Jeff Wright, the Dean of Merced, is here today. Merced has done an enormous amount for conservation and energy efficiency in the design of their buildings. I ran through the kind of power-aware building stuff. I showed you that cartoon of my wife. I mentioned the work of other folks in the server farms. I showed you the fuel efficiency work on combustion. That example of improving, say, the BART system, so there's a bus there to work with you as soon as you arrive. I went through some of these exciting environments of biofuels and biopower. I stressed the emerging safety of nuclear energy. I stressed the importance of turning coal into other fuels, not just directly by pulverizing it and making it straight into electricity. And I stress this opportunity of capturing the carbon at the top of these particular power plants that I mentioned in the Ohio River Valley and storing it. So there's a very wide portfolio of opportunities that are in our CITRIS work, and we're going to be addressing all of those in order, as I said at the beginning of my talk, to not only give us our cake, the energy that we need, but to eat it too, and to make a safer world, and to reduce the emissions to the atmosphere as shown there. Because, as you've seen already, unfortunately, in my first slide, it's hard to find a good planet. It's the only one we have, and we want to keep living here in a wonderful, energy-efficient way, but we want to treat it with respect and love its environment. So thank you very much for being here today. Thank you.